So we will start with section 4.4, which is on spin. And you know this property of a body. One is orbital motion. Orbital motion is when a body rotates around the axis of another body, and spin when it rotates around its own axis. So you will have to differentiate between the two. Like our Earth is orbiting around the Sun, and it is also spinning around its own axis. So we will have to keep this thing in mind. And from where this property comes in, if you remember, we have covered the angular momentum portion, and inside the angular momentum, we studied that L is R cross P. While when it comes to the spin, then it is I times omega. I times omega. This omega is the angular velocity, while I is the moment of inertia. You know the moment of inertia. Moment of inertia you can, in other words, call the angular mass. And I have explained this thing in the conceptual physics series in the rotational and translational dynamics. If you want, you can go through those videos. So in the angular momentum, we came to know that while solving this, we came to know that there are means the L, which is the orbital quantum number, is minus L plus N. I can write this thing is N is equal to 2 times L. And as N is integer, so from here this comes out that L can be N over 2 as well. Like it can have half integer values as well. You remember, we were having the values of L, they were starting from minus L, going to 0, and then plus L. So, they were running in integral steps. If I write this L equal N over 2, then half integer values are also possible. So how this thing we will realize? Because when we wrote our psi as a function of r, theta and phi, when our psi is a function of r, theta and phi, then from here we just derive the values of L and M. And both L and M were integers. Both L and M were integers like 1, 2, 3. But here we came to know that the half integer values are also possible. So how we will cope with this situation from where the half integer values are coming in? Because we studied the spherical harmonics, we studied the psi as a function of r, theta and phi. So additional values are coming in. And now those additional values are half integer values. This we haven't derived. Because in our solution to the Schrodinger wave equation, from where we derived all the quantum numbers, the L and M were integers. And now this condition tells us that we are having half integer values possibility as well. And this half integer values we will attribute to the another angular momentum which we call the spin angular momentum. Now we will have to clarify few things that why this situation we are facing. The very first is that when I consider the elementary particle electron, then electron is a structureless particle. It has no structure. You know its diameter is approximately 10 power minus 18 meters. When you don't know the structure of something, it is a structureless particle, then how you can say that it is spinning as well? So physically electron is not spinning. Physically, electron is not spinning. Because in order for the spin to be physical, it should have a structure. But it is a structureless particle. The electron is a structureless particle. So physically it is not spinning. But it is having an angular momentum which is just like a classical particle, which is just like the classical spinning. And our mathematics is telling us that we should have some angular momentum value, which is the half integer values they are coming in. So why there should be a spin angular momentum? Here it says that there should be a spin angular momentum, and here it says that physically it is not spinning. So from where it is getting that angular momentum? We would have, if we would be able to see this electron, to break this electron, means its structure is defined, it is having some structure, then we would have differentiated that this is the orbital angular momentum and this is the spin angular momentum. But it is not possible, it is structureless. So we will have to follow our mathematics that how this thing is occurring, how this angular momentum is there. We will have to go back to the 1922 when Stern and Gerlach, they were having some experiment about the finding out, means they were not doing it for any measurement of spin, they were doing it for measuring the magnetic moment of an electron. And they observed something. They observed that they selected a specific beam of elements, and they selected that when there is no role of orbital angular momentum, like L is equal to 0. So you are having L equal to 0 means only the S orbit. And S orbit of any element, you are having the orbital angular momentum equal to 0. So there is no role of orbital angular momentum. And they wanted to measure the magnetic moment. Magnetic moment, you know what is it? It is denoted by M, and this is equal to I times area. I being the current, and area is the area of the loop. Is in pair set, if you are having a loop and the loop is having area A, then if current I is flowing in this, you will have the magnetic dipole moment equals to the current times the area of this loop. And this is a vector quantity, m equals I times A. So magnetic moment will be in this direction. When you place this dipole, this is a dipole, and like you're having south and north poles in a permanent magnet. But in pair defined, this is also a dipole, south and north means two poles. Ampères defined that this is the magnetic dipole, current carrying loop, and its magnetic moment will be I times A. When you will put this magnetic loop in this current carrying loop inside a magnetic field, it will experience some torque, and that torque will be equal to M cross B, magnetic moments cross multiplication with magnetic field, and it will experience a force, like it will experience some rotation, some torque, and it will experience some translation, some movement which is equal to force, and this will be equal to mu times mu dot gradient of magnetic field. This will be the force that it will experience, and this will be the torque. Both of these can act, means it can be displaced inside a magnetic field and can rotate as well. So, we are having, consider now the same situation on the electron. Look, when you consider an atom, it is having a nucleus and the electron is going around it. So electron is a charged particle, and you know when charged particle moves, it generates current. So it is just like this one. It is a tiny current loop which is here. If I place an atom inside, means it is a tiny current loop and it is possessing some area. So it is having some magnetic dipole moment, and it will have some direction as well. So when I place an atom inside a magnetic field, it will experience a torque, it will experience a force. So I will have to find out that how much force it is experiencing or how much torque it is experiencing. And this was actually the job which was done by Stern and Gerlach. Right? This was the job that they did. So in order to exclude this thing, which is L equal to 0, you know about the Zeeman splitting. Zeeman splitting, when you put an atom and you are observing its emission spectrum, you see that the single line inside a magnetic field splits into many. It is called the orbital splitting. Means inside an orbit you are having many orbitals, and that splitting occurs there due to orbital angular momentum, due to this force. When you place the same atom inside an electric field and you experience some splitting, that you call the Stark effect. Now you are having the fine splitting as well, hyperfine splitting, and that splitting is not due to the orbital but due to the spin. So you will have to remove the orbital. So I will consider some elements, like for example I consider the L equal to 0, like hydrogen, I consider. Then hydrogen is having s orbit. I consider all the s orbits like hydrogen in such a form that only the electron is in the s orbit, not in the p-parallel, means non-excited hydrogen atom. So the electron lies in the L equal to 0, the s orbit. And I pass on to the magnetic field. And if I observe something, then it will not be due to the orbital angular momentum, but due to the spin angular momentum. So the magnetic moment of an electron, I can write is in terms of the angular momentum. I will not derive this one as you have done this thing in electrodynamics, and it will be L. This is from this equation, means here I am writing M, here I am writing mu. So they are the same thing. Let me write this M so that you are not confused with this. So it will be equal to this, where E is the charge on the particle, M is the mass of it, and L is the orbital angular momentum, and the force I can write that this dipole, magnetic dipole, will experience a force M dot gradient of B. So you can write, if you consider its x component, here it will be curly B by curly x. If you consider y component, then it will be the y component of this, the y derivative, partial derivatives, and so on. So we say that our magnetic field is in the z direction only. So its force in z direction will be M dot curly B over curly Z. And this will be magnetic field we will apply in the z direction, like here. We will apply the magnetic field in the z direction. This is the magnetic field. Now, why do you specify the magnetic field in a given direction? Because when different orbits will come in, means electrons having in the different orbits, so those orbits will get some deflection due to this magnetic field, which is fixed. When I will consider the N equal to 0 orbit only, like I select only those elements in which the electron is only going in the s orbit, there will be no contribution from the dipole moment of the orbital angular momentum, right? So there will be only, means they will not be here. And when I will pass such an atom inside a magnetic field, it will experience this force. You see here that M will have any direction, and it will be dot multiplied with this one. So what the Stern and Gerlach did in their experiment, they selected an electron gun like a source from, let me do it here, like this is an electron gun which is producing some electrons, and the electrons are coming this way, and they are passing through some slit in order to make the beam narrower. So this is a slit, and after this one, they were having a non-uniform magnetic field like this. This one is like this, so the field there is becoming non-uniform. Like you consider such a combination. If they are both are flat, the field will be uniform. So we are passing them through a non-uniform magnetic field. And when the field will be non-uniform, then we will have some force there. When the field will be uniform, it will only be torque there. You know this fact from your electrodynamics. When we will use uniform magnetic field, torque will be there only. And when we will have non-uniform magnetic field, then force will be there as well. And we are studying that force. So what happened? That here they were having a detector, and they observed that when this beam can be of hydrogen, because hydrogen is 1s. This beam can be of silver, because in silver you are having the configuration is such that you are having 3s1, and it can be potassium, it can be copper, it can be silver, and cesium and gold. What the Stern and Gerlach selected, they selected silver, in which you are having 5s1 electron. Transition metals, you know, they are having 1 electron in its outermost shell. And that 1 electron in the non-excited state will lie in the s orbit, and they are in the 5s. So they selected the 5s orbit, and you know that it is having 0 angular momentum. And when this beam passed after the magnetic field, then no electron moved straight here, but half of the beam went there and struck there, and half of the beam went there and struck there. So this was quite surprising. I mean, such kind of splitting was never observed earlier. And this wasn't explained by the classical physics or the physics so far we have done here. It wasn't, means the physics till that point wasn't able to explain this kind of splitting. Because in Zeeman effect, the splitting was there, and that splitting was actually due to the orbital angular momentum that we considered the L non-zero.